All right, everyone. Hello and welcome to another day where we do game engine in Go from scratch. Let's wait a bit for people to come. Nice. Hey, welcome to the stream. All right, let's see where we left off last time. While this runs, as always, for the first time, this takes a while. Not sure why. Maybe it's building all of the GL stuff. The C code is too much. Okay. So last time we were working on buffers and we did all this buffer work, data type, and we were switching, and I think we'll change all of this from compatibility to core today. We were, let's see, we made this buffer type, right? We made the buffer struct, and in this case, we hard-coded kind of two buffers for each vertex. I think I want to change this, and instead of passing it one by one, so for now it's okay, but the way we would actually load objects, like when we load a 3D model, it's not going to look like this, right? Like the 3D model file is going to come in with the vertices, vertex positions, with the color, with the normals, vertex normals, all of the information packed together. So in fact, it's closer to us kind of getting all that info at once than someone kind of filling in one by one. And it might make more sense for us to have a buffer object, like one single big buffer, which has everything on it. So instead of a buffer for the vertex positions, a color buffer, we just have everything kind of interleaved together. So we're doing this last time, right? So if we have, it's too small. If we have our buffer like this, instead of having two buffers, like X, Y, Z position, and then again, X, Y, Z, and so on, and then another buffer on the GPU with like the colors, right? The vertex colors, R, G, B, etc. It might make more sense, potentially more performant, for us to put all the information of one vertex in one place, in the same buffer, right after each other. So you have all of this is like vertex 1, and then all of this is vertex 2. And so instead of having vertex and then another vertex position, we actually do, let's say we have color and position. So you have the position and then the color info, and then the other vertex comes in, which also has position and then color and so on. Then we only actually generate one buffer and we only fill in one buffer. And the way we tell the GPU is by having like, okay, where does the color start? It starts as an offset from the beginning of the buffer. This is 0, 1, 2. So this is an offset of 3, right? And then our stride changes. So our stride, the from the beginning, before the beginning of one, let's say, position to the next position is just the length of that. But now the stride is actually is all of this. So the size of one full vertex of information before we get to the next one. So we might do that. I'm going to leave it for a bit later, maybe today. Not now. Let's do something more interesting with the stuff we have on screen. So we did this. That's our nice little colored cube, which we are filling up in main. So we did this load buffers. We have kind of our vertices or colors, and then we generate a buffer object and then fill in, like to that buffer object, we do two buffers, right? And this handles all of the VAOs, etc., for us. I just want to go ahead and first just move everything to core. And I hope this doesn't kind of take too long for it to load. I think it's core. I think it's called core. Let's see, actually. Oh, yeah, I think it's called core. We don't want yeah, it's called core. 4.6 core. Cool. So it's just loading there. Here, do the same thing. The info compatibility has gone. And then this as well. Wow, Go is really struggling today. Or other VS Code, I think. Let's see, where else? Shader programs for sure. Need this. Okay. And our shader, I think that's it. This should be it. Come on, Go, you can do it. You can do it. Can we cancel this? Did it actually save? Oh, it did. I think. Okay, this worked. Don't know what all the loading comes about. Okay, let's see now. Go on. I think it's going to take a long while again because we changed it to core mode, so it has to do all of this stuff again. But today, let's actually have some movement. And we're going to do uniforms. Should be easy. So if we look at our shader, let me just close all of this. We look at our vertex shader for now. We load the vertices in one position, and this we'll be doing over the next few streams, I guess. We need to move stuff around. So we need to kind of take this object, this 3D, 2D object, whatever it is. And if you export it from a 3D program, it's going to have like the vertices around some origin, like the center of the object might be 0, 0, and then all around it, it's maybe 1, 1, and so on. So some kind of position. We need to move this into a world position, into a world position where all the objects live. So we need to transition these positions into some different position system so it can exist next to other objects. And then there are multiple transformations which you can talk about, which is the MVP, like model, view, and projection matrices that need to happen. So today, at the very least, I want to do the model matrix, which allows us to kind of scale, translate, and rotate our object. Okay, so core mode is working fine, right? So what we need to do is we have this. If we want to move stuff around, we can obviously change the position, but we don't want to load vertices every single time to the GPU. That's too slow, too much work. So instead, we are going to do this work on the GPU. So on the GPU, in the shader itself, in the vertex shader, we have kind of the vertices coming in. So our X, Y, Z coming in. So there's a single vertex, and we want to draw that. Before we draw these positions, we are going to move them around. And the way we're going to do that is we're going to have a matrix that has some values, like it's a 4x4 matrix. And I'm just going to have the identity matrix. This is 0. So if this is called a transformation matrix, and I don't want to go into all of the math. Transformation matrix, right, which encodes a lot of information, including the movement of the object, the scale, so bigger or smaller, and the rotation, all in one matrix. So in one multiplication, we can move the vertices so that it looks as if they got bigger or small, like the object got bigger, smaller, rotated, or moved. Now, in this matrix, at least one part that's simple from this matrix is, if you multiply by this matrix, nothing is going to happen. It's just going to stay where it is. But these actually encode the position. So this number is the x position. How much to move by x in the x-axis. And this is the y position, and this is the z position. So simply by having this matrix and changing these three numbers, we can actually move our object in the game world. And now all these matrices, we are going to need a lot of matrix math and vectors and whatnot to both do the game and to do the graphics rendering. And the best library especially for 3D graphics that I know of is GLM. Right, it's called GLM. It's very well known. It has like 4,000 comments, right? It's active still, and it's been there forever. The problem is, it has all these specialized stuff, matrices and vectors. It has stuff for drawing. It has stuff to give us actually a transformation matrix. So we don't have to build it or understand how it works on a deep level. We just kind of use it to move our object. The problem is this is in C, C++. There's a lot of templating and whatnot, and Go cannot work with that, unfortunately. I don't know what's wrong with your today. There is a lot of templating. We cannot use this. I searched a lot. It doesn't seem there is a straightforward way to use this in Go. So I went ahead and I started making my own library, kind of inspired by that. I spent the last few days doing it, which I call GGLM. And it gives us a lot of the stuff we might want, like matrices, vectors of all types, operations, and even transformation matrices. I'm going to import this and use it. So I haven't really used it before. I have the kind of the math, and it is all correct. I tested as much as I could, but let's see. So now I want to get this and then create our transformation matrix, which we will send to the GPU, to the shader, and then the shader can use it. Right. Now, first, OpenGL itself does have matrix and vector stuff. So like we already use vectors. So this is like a vector 3, vector 4, four elements. We can actually do matrices. Like I can get a 4x4 matrix just by doing mat4. And we can call this the model matrix, for example. Now, some information like these in the in stuff, vertex position color, is per vertex. So this shader is going to run for n vertices for each object, and it's going to receive different information for each one. But if I want to move an object, like let's say 5 meters to the left, I don't need a matrix per vertex. We just need one matrix that is shared, like a global variable between all the vertices that are in this shader. So if we do in, then each single vertex is going to need this matrix again and again and again, but it's the same matrix. So we don't want to have it like this. So there is this thing called uniform. And all this means it's a very similar way compared to filling this. It just means it's a global variable that we put in this shader. All the vertices shared. Doesn't matter if it's vertex 1, 2, 3, if these things might change, but this thing is constant until we update it from our code. So there are calls to set the different kind of variables. So here we called it model mat, right? So let's say here we can do gl dot uniform. So there are functions to set all kinds of uniform. So ours is a matrix for FV, right? Which takes a location very similar to before, right? We need some kind of location. How many matrices we're setting? Just one. Do we need to transpose the matrix? So that's true or false. And then the matrix itself. Now we don't have the location. Location is very similar to getting the attributes. It's just GL, I think, get uniform location. There we go. So we give a program. In our case, it's a shader ID. That's our program. And the name is model mat. And we put termination there, an null termination. Then we do str. So it's very similar to setting attributes. We don't need to activate them. They're always there. And we use this location. Now, if you noticed here, we did not specify which shader. Like I might have two shaders having the model matrix. So which shader are we setting this on? And this function operates on the currently active shader. So once we do kind of activate, and then we set it here, this information will be set. But I think this is a relatively new one. There is a nice, I think, program uniform matrix, something like that. Let's see, program uniform. Yeah, uniform matrix for FV. And this thing takes a program. So it doesn't matter if the program is active or not. We're just saying, hey, for this specific program, set this uniform. So for a test, just to test. So we have this. We have our model matrix. We're not doing anything with it. So if we run, we should get the exact same stuff that we get before there. So now to move it, to apply the matrix, we multiply this matrix by the vector. So luckily the multiplication math is built in, so I can take this, multiply it for vertex position. There isn't anything special here. We kind of, because of this special arrangement of the matrix, going to do something to it. Now, because we didn't set any values to this, it's going to multiply everything by 0, and so we'll get 0 position for all the vertices. So they're like all shrunk in the center of the screen. So we should see nothing now if we run. Exactly. We see just a black screen. We don't see anything. So we want, for a starter test, we want the identity matrix where we're not going to move the object. We just want it to keep it where it is. So this happens by just having the diagonal set to 1. So I'm going to do this by using the library I made, gglm. Right, and then we can say a new transformation matrix identity. So a new kind of identity, no movement, nothing. So it's called model matrix, right? And we can print, we can see model matrix dot string to print it in a nice way. Let's just look at that. So we have kind of this matrix, all ones in the diagonal, nothing else. Now we can take this at the very start, so we don't do it every frame. At the very start, we get the uniform, and we're going to set it. We're saying, hey, this uniform, we have one matrix that we're setting. It's not an array, basically, of matrices. Transpose, yes. So transpose just means, are you storing it row by row or column by column, which is not shouldn't matter really for anything, just convention. And then the value. So the value is just model matrix the data 0. So we're sending a pointer to the first element, the data, and the data is an array. So it should work. So now this matrix should update the uniform value, and then when we multiply any vertex, when we draw, it should just keep it in whatever position it's in. And here we're starting to get to some really cool stuff where, hey, we're doing something with the drawings. We can move now, we can do things. So there we go. So we're actually multiplying, but it's staying exactly the same position. And now we can start playing with it. So if, for example, we do model matrix translate, so I want to move it a little bit. So I'm going to move it by, let's say, a bit to the right. So let's say 0.5 to the right, and then nothing on the other axis. So this dot translate is just going to change the translation values, right? So it's going to update these for me. So we'll see now. We have movement. We are actually moving stuff. That's amazing, honestly. So this has moved. It retained the shape, just translated to the right, and we can see that this value alone has been moved. And of course, this one signifies also the scale to make it bigger or smaller. So we can do that. So we want to translate, and then how about we scale? Let's see. So let's scale everything by half to make it like half as small. And then let's see. So we should see now all of the rectangle. There we go. That's it. That's really all there is to it. Now there is we can get what do you call it? We can get a rotation matrix. So new rotation. Rotation is a bit more complicated because it uses this thing called quaternions, but there is an easy way. So we can say get me a new quaternion. So quaternion is kind of a four-dimensional, like a vec4, a four-dimensional kind of mathematical object, you could say, that is used to represent rotation, and has some very nice properties compared to just XYZ rotation. But then we can use it along with this XYZ. So let's say, so X is left and right, Y is up and down, and we want to rotate around the center axis, so the Z axis, and let's say we want to rotate it like 90 degrees, right? So we're going to say I want to rotate 0 on X, 0 on Y, and 90 degrees on Z. That should give us a new rotation matrix. Now, I think normally the rotation matrices have to be applied in a certain order. So we kind of have to scale. Usually we scale, translate, and finally we rotate. Actually, no, we rotate, scale, rotate, and then translate. Okay, so translation is the last step. So we take the matrix, we scale it, then we need to rotate it. So rotation matrix, and then finally we translate it. Now, actually, all of this is done in three. It can be done in three distinct steps. So we have our model matrix, which is just identity. Then we have a translation matrix. We want to do it kind of step by step. New translation matrix. So we said we want to move by 0.5 on the X, 0 everywhere else. And then we have our scale matrix. New scale matrix. And we said we'll do everything is 0.5 on all axes. And then lastly is our rotation matrix. They're independent matrices, but they're all 4 by 4, right? So then we multiply them to get one matrix that has all the combined effects of all of these. So one matrix that has only translation, one has only scale, one has only rotation. We multiply them in a certain order and we get the combined effect through one, basically one multiplication in the end. So in the end, we just want to multiply one thing and get all the things, all the operations combined. So the way we combine them is just multiply them. So we have our model matrix, which nothing has been done to it. We're going to multiply in this order. So we're going to do multiply by translation, which multiplies by rotation, which multiplies by scale. So the order is actually scale matrix multiplies with the rotation first. So we are kind of scaling and then rotating. And then the scaling or rotation is multiplied by translation. So we scale, rotate, then translate, and then all of that is multiplied finally with the identity matrix, with the final model matrix, which we can load. And if we look at that, which is hopefully correct, we get an interesting now matrix. There we go. That's not 90 degrees, but it did something. But we can see this is applied here. Scale seems to be done. Yeah. Let's see. Potentially the order. I think the order is correct. Model. Let's try without scale, just to see kind of what the issue is. Because again, this is a new math library, you might need to do some things. But yeah, I think rotation is not really correct. You can look at it online. Let's do without scale or without translation. Yeah, so it's not really rotating correctly. Oh yeah, so quaternion Euler takes the rotation in radians, not in degrees. So at the very end, I can do as right radians, right? And now this should give us perfectly 90 degrees rotated. Nice. So I think this red is now down. Which was up. Let's look at let's do the zero rotation. It's ready to be kind of up facing. So I'm expecting 90 to mean the red goes on the top right instead of it's kind of rotated opposite to what I was thinking. I think because the z-axis in OpenGL points outward, so we have to kind of do minus. Yeah, but this is like flipping. This is not rotating. Are we rotating around the wrong axis? Maybe. Let's try different axes. Nope, wrong axis. That's very odd, because it does seem like it's flipping. It's rotating too much. Yeah. Actually, that's it was correct. Yeah. That's correct. I think 45, and then 90 puts it on the. Does it? This is halfway rotated. Yeah. Okay. Yep. This looks good. So let's say let's scale it on the x-axis by double. Let's get this back to 90, and let's move it by. too much. Let's scale it by 2.5. 0.5. There you go. Nice. Yep. Cool. So we kind of have control now over the scale, rotation, and translation of our objects, whatever it may be. So 3D object doesn't matter. We just multiply by this. We just need kind of to put this code on the shader itself. So I think on the shader object, shader program, just like we have set attribute, enable, we can have a what do you call it? Set uniform. Let's follow the set uniform mat4 and we take a string and I'm not sure whether to take an array, honestly, or to take the object. Let's take the object to keep it simple. I am not sure. Should we take an array? Uniform name, right? And then the data, we need to take the data. We might as well use this, I guess. Yeah. So let's take a mat4. Right, and this is the mat4. And then you can just take this, plug it in here. Location is sp.id, and then here we have the uniform name, get location, then set the matrix, we transpose yes, and we send it in. That should be it. For now, we might as well just do a couple more. So uniform maybe vec4, something you might want. Vec4, but here it's a program uniform vec. Uniform. I think 4f is basically vec. Yeah, 4f. That was the issue. Oh, it wants separate codes. Can I send one thing? Yeah, there we go. What's the problem? Oh, there's no transposing. Yes, there we go. Let's just confirm what this is. What's all this? Yeah, I want the docs piece. Number of elements is not an array. Yeah, I suppose. A new value for vector and matrix. Yeah, to an array. Exactly, this is what we're doing. So this should work. And f by location floating points, yes. And where's the b? A float, yes. Okay. An array of matrices. Yeah. Okay. So I think in this case, if we have a, should say 2, right? 2 for vectors. Yeah. So it seems. So we're saying uniform 4, but we're telling it it's 4. I mean, we can test. How do we test? I mean, we can have an offset just to test. The vec 4 test vec, and we can kind of add tiny amounts to this one, shift it maybe down. So, all right. So all of this becomes simple shader dot set uniform matrix 4. Add. And here is our model. So matrix. And this is gone, this is gone. And we also need to set this one. This vec. And let's create a new vec 4, right? And let's just offset select translation. So we'll offset 0.5 on the y-axis. So the W component should usually be 1. But we are adding, this is already 1, so let's make it 0 in this case. Okay, let's see. Did it boom down? Not sure. I don't think so. Test this back. I don't think it did. So I think this should be 4F. Components. Right, so instead let's put this as 4. No, so it's not really moving it. Let's put a big delta, so delta minus should disappear. Oh, x, y. Yeah, I mean, it did move, so we know it's being sent, so 1 should be correct. All right, you can move this now. Go away. And we don't need this. All right, cool. So now again, we have our translation matrix. We have some uniform code to set that, at least for vec 4s. You know, obviously, can literally just copy paste this and just change 4 to 3, and we have this. Instead of matrix 3, matrix 4 becomes matrix 3, and same here. We can do 2, 2, 2, then that's it. Yeah, let's just do vec 3 and vec 2. Right, and then here uniform 2f and vec 3. Well, so vec 2, 3, 4, and 2, 3, 4 for matrices. That's it. That should be it. So we have our vertex. We can scale it. Now it's not complete as far as the kind of showing it goes, because you can see even when we rotate, so if we rotate like 45 degrees, it looks kind of odd, right? It looks kind of skewed. Anyway, it was longer before. Now it's a perfect square. Rotated. The original one, it should be double the size. So this is because we don't have all of the matrices we need. So we need 3: MVP, model, view, and projection matrix. And essentially we have a camera, right? It's not really good thing, but yeah, we kind of have our camera, if we think of it as if it's our eyes, and so it will only see what is between these two boxes, right? And the things that are further away and closer, like closer things should look bigger, and then smaller if they're further away. So this is to move the object from some arbitrary, like, okay, the center is actually the center of the object. This is the model space. We need to move it into world space, where the 0 is not actually the center of the object, it's the center of the world, of the entire game world that we have. And so you kind of imagine if we have our game and we want to draw kind of, this is too strong. We want to draw like some cubes, right? Like this, one next to the other, and then maybe we have a sphere at the top and so on. These are put in relation to each other according to the world position. So this might be in position like 10, right? 10, 5, 0, and then this is, I don't know, this is like this is 13, 13, 7, 0, etc. Right? So they have some position in the world. But if you look at a 3D program like Blender, it's not actually like this. The position of the object is according to the center, wherever it may be. Usually somewhere on the center. This is 0, 0, 0, and then this one might be, let's say, I don't know, 1, 1, 0. So these are the vertex positions, and we need to move these vertex positions so that they go from this to this vertex here, actually being, if this is 10, 5, 0 in the center, then this is potentially 11, 6, 0. So we moved from a coordinate system where the center and the vertices are somewhere else, like compared relative to the object which we are building, So each object, and this is called local space or model space. This is local space. We're moving them to an entire world where everything exists together. This is the world where we build our game, where things move and so on. And we do this by multiplying by the model matrix, which we did here. Right, this transformation matrix where we have translation, scale, and rotation gives us a model matrix, which we then multiply in the vector. Now this moves into model space, and then we actually have more. We have two more. We have a view matrix and projection matrix. And I don't completely understand these two yet, but the multiplication is going to be in this order, essentially. So using this, we move into from the space of the object, local space, to world space. And then by multiplying again with the view matrix, I think we move to kind of the screen, like the camera view. And then projection is orthographic or what do you call, like a projection matrix. So perspective, right? Perspective projection matrix, like this one. So perspective is like how we see in the real world, where things closer to us are bigger and things further away are smaller. So and it looks like this, right? So you have an expanding kind of view as you go further. So there is again a special matrix. I haven't implemented this yet into GGLM, which we'll need later on. So we need this, and then we have as well the view matrix. Where is this? Is there any good? Oh, this is a perspective matrix. Let's look into. I think, is there an OpenGL down? I have no idea. Yeah, okay. This we don't need. Yeah, so we have this. Yeah, so we need to implement this with time. If view is affected by where the camera is, and then we have the projection to give us the final kind of coordinates in OpenGL. Yeah, no, OpenGL is completely down. Okay, so we'll do these later. I want to kind of start using our engine a little bit to do things. So we might actually implement loading now. So we have our shaders, but what if we want to load some sprite, for example, or a 3D object? And then instead of having these here, we actually load them from an object. So we can create something like loader.go, right? We'll just load up J. So we need to write some loaders, and we might end up using a library later on. Or at least when our obj files are simple and we can get them from Blender. Obj file format. It's a very simple text format. Not the most popular nowadays, but it's okay. Like, it's a good start. 3D tools can open it up. Let's get Blender. We need it. Come on, Blender. Right. So we have this. So if we have designed in a 3D modeling software, so where is the edit mode? And let's get faces. So I might have built, maybe I built something, say, oh, oops. Right, maybe we have some model of whatever number of vertices that are needed to, maybe it's even like this. some model like this, and we want to load this model or maybe it's a character into our 3D game engine. So we're going to export as an OBJ file. I think FBX is one of the most popular nowadays, but it's more complex. So maybe we can start with OBJ just so we can actually have something to write. So we have OBJ. Let's save it somewhere. So we say, you know, it's object.object, and let's see. So we want, so here we have now some settings. Right normals, yes. Triangulate faces because we are only dealing with triangles. And let's see, apply modifiers. I think forward is minus Z, Y is up. I think this is correct. And we are just exporting the OBJ file, right? Export. The nice thing is OBJ is literally just a text format, nothing else. And so we can actually, let's go to resources and just plug it in here, I guess, or models. Right, just for now, have it here. Now let's read. We can open it up. It's a very simple text format. We have highlighting for it. OBJ grammars. Hey, that would be cool. Actually, that's not. So let's read. So os.read read file. Okay, file, and we have b error and returned, or not, just an error. Right. If error equal to null. Right. So you have the bytes. It's done. And let's get our model. So this is the model. You can actually see it's very cool. These are our vertices. So you have some stuff, some comments we can ignore. Where is your MTL? I think this is the material, which we don't care about right now. We have the name, again, O. The things prefixed with V are the vertex positions, if I'm not mistaken. So these are the vertex positions that we want to use. And then we have VT. I think these are the normals. Will be important when we do lighting on our 3D objects. That'll be very cool. Material. And these are the faces. These are the actual triangles. So this is like triangle 0, 1, vertex 0, 1, 2, 3, 4, 5, 6, 7. So 7 vertices, so 0 to 6. 0, 3, 4, 5, 6, 7, 8. Yeah, 0 to 7. Other 9. Let's just read a bit more about the format. So OBJ. Okay. Comment. Vertex. Okay, so VT is texture coordinates, basically UV. So we are not going to load that now. The nice thing is we can choose what to load, the things we want to load. The normals we probably want to load soon, and then the vertices. W is optional, defaults to 1, sure. So right now we care about these, and then the face elements and the line elements. Not sure about the face, list of vertices, texture, normal indices. The format, vertex, texture, normal. Okay, starts at 1. Okay, vertex, offset. Okay, so because we need to. I don't think we have done elements so far. Yeah. For now, we're just drawing literal kind of vertices. It's okay. So let's load this. We don't have a data structure yet for all of this stuff. So we might let's put this here as is models. Right. Let's read it and let's produce, for now at least, a list of vertices. List of vertices. Right. Yeah. Let's return float 32. Right, this is our outputs. So outverts is a float 32. Right, empty. And then we can go line by line. We have read lines. IOUTils read. Line. I remember there being one. File, but that's okay. So we can have lines equal strings dot split v on the new line. Correct. Right. So we have our lines, and we can then loop len lines. We're just going to extract for now the list of vertices. And if the very first character is v, so yeah, essentially we take this, but then some of them are multi, and these are our triangles. So this is vertex, vertex, vertex. We can ignore these two for now. So we can, I don't know, it's called command, and we can do strings dot split n. So let's just take the first part of that line. So lines I, and do this, and we just want two. So we just want the left part and the right part for now. And let's take so command or LR, right? So split. So then we can maybe switch on mod, so we can switch on the very first part. And if the very first part is, if it's V, then this is a vertex, right? Otherwise we can ignore it. So we can have a default that does nothing. And if it's a vertex, then we can split by the space, right, of each one. And then this is our X, Y, Z, I assume. And so we can do outverts. Actually, first we need to process it. So we can have verts, vert was strings dot split, split S1 again on the space character. And if vert was strings, now we need to loads dot parse str convert, I think. So if it's float, parse float, converts the string to floating points. Exactly. So we know there's always 3. We don't care about the last one for now. We'll just make it vert plus strings. We just make it 1 always for now. So 0 bit size 32. Yeah. So f error if sorry, turn null and f, right? Otherwise, we can append. We can say outwards equals append outwards, and we're adding f. Why are you? Oh, yeah, we can do 32 f. That's it. So now we can just repeat this because we know we have three these are not new anymore. We have three. If it's a v, then we have three positions: 3, 1, 2, 3, so on. Otherwise, we'll ignore everything else. We'll ignore all of this. Yeah, that should be good. And in the end, return outwards. And now, let's see how this does. Null error. So let's load. Maybe in, yeah, after all of this, load. Okay, so let's do loader. This is called models dot load obj, and the file is resources models object. And we can get vertices from that object and an error. And if error becomes null, I just panic. Right. Otherwise, for now, it's just print out vertices or object vertices to confirm that it's actually loading. Okay, for logger. Log dot printf. So let's print like as much details as we can. But this, let's not print the matrix. Let's load. Let's run. Okay, so I think this is correct. Let's confirm with our objects. So we have 2.27, yes, 1, 0.3, yeah, then 3, minus 1, 0.1, and at the very end it's minus 1, minus 1, 1. This is actually correct. This looks like it worked fine. 0.75, yeah, this is good. So we have vertices. So instead of doing this, now let's just not rotate. So we can see it normally. We just do this. We shrink it by half. But otherwise, let's center it as well by editing these translation matrices or transformation. And then let's take this object loader. Right, and let's put it right here. So our stuff is in the same format so far. So we have three vertices, like XYZ into each. And so we can, I think, directly substitute. We can literally just say vertices equals object verts. And let's see, we get our object. Okay, I think it's something. And obviously it's not going to show correct because it, what do you call it? It's not a proper 3D projection yet, but we can confirm. So I'm not sure how it's being looked at. I think we're seeing maybe some part of it. yeah, we're seeing it like this, in this kind of direction, but like zoomed in this kind of way. Not sure. Is it like this? Yeah, let's shrink it more and just make sure. These colors might not line up anymore, by the way. So for now, let's not put a color object, because we might have more vertices than before. This is only 1, 2, 3, 4, 5, 6. We have, I think, one more vertex than before. Ooh. We have a bug. In buffers, go 42. Okay, I think it's expecting a color all the time. Buffers, go 42. No, this should be correct. It's just a bind. Is there no ID? Who's calling it? Set attribute. Oh, we are setting the color attribute while we don't have it. Where is this? Set attributes. There we go. We don't need this anymore. Not yet. By default. You know what? Let's load the colors. Let's do it. Load the colors and avoid this mess. So, oh yeah, and we need to actually do these elements, something we don't have yet. Yeah, so I think this is very important. Let's do it now, and then we'll care about UVs or normals or anything else. So one last thing that we actually need for rendering, and for this, we can just revert to the original cube we had. There we go. If you notice, if you look at this, we have two vertices. We have some vertices that are repeated information. That's not actually required. We have here 0.5, 0.50, and again 0.5, 0.50, which makes sense. If we look at the drawing of a cube, right? Where is the? We have one, yeah. So we said everything is triangles, and a cube, for example, is made up of two triangles. Sorry, not a cube, a square. Now, this vertex, right? These two vertices, this one and this one, at least in this case, are repeated. So we have 6 vertices, while in fact we need 4. That's it. We need one here, one here, one here, one here. But we are adding 2 more because, like for example, this vertex is copied once for this triangle, and then there is another copy of it for this bottom triangle. So there is, now this is basically wasted memory and processing power, more vertices to process for no benefit, at least in this case. So there is something called an element buffer, I think. So we don't draw triangles. I think it's called elements. Yeah, draw elements, something like that. And the idea is we load our vertices, and instead of specifying literal vertices to draw, we specify indices of vertices to draw. So if we want to draw this cube using only 4 vertices, how do we do it, right? We can actually do the following. It's a simple idea, but it's very, very nice, powerful. We have vertex 1, vertex 2, 3, and 4, and we want to draw this cube these two triangles, right? This is triangle number one, triangle. I want to draw them using only 4, not however it becomes like 6, right? We want only 4, not 6. So instead of sending 6 vertices, we will send 4, and then we will send another list of integers. The list will include indices. So let's say this is index 0, vertex 1, vertex 2, vertex 3. So we won't draw the vertices, we will send another array including indices of triangles. So we will say, for example, here, we will say, what is our first triangle? Our first triangle is index vertex 0, and then 1, and then 2. So we're drawing in this kind of, sometimes the direction matters. So we have 0, 1, 2. And then in the same array, what's our second triangle? It's the same vertex, 1, 3, and 2. So you can say then 1, 3, and 2. We don't have duplication of vertices anymore. This signifies triangle 1. This signifies triangle 2. So this reduced the number of vertices required. And you might say, hey, okay, sure, you know, but you introduced an entire new array. Sure, but remember, a vertex isn't just 3 floats. It's a ton of floats. Like this, all of this is only 7 vertices. 7 vertices, but then for each one, there are also UVs, and there are also normals, and then we also have colors. So each vertex includes a ton more information if you copy it. But on the other hand, if we just have indices, it's way less info compared to that. So we want to have this. We want to draw not through direct arrays, but actually through these index drawing. So let's go into, I think, our shader program, where we have activate is used. What do we do? I think I have a draw call, right? Draw arrays. GL draw elements. This one. So this is the, I think the other one. This is drawing. You see how it says indices? So it wants the indices of this. Let's try. I'm not sure if we can do it without additional loading the GPU, but mode, it's again triangles. We're not doing anything else. No. How many? I think 6, right? And I think it's GL floats. Not really sure. And then indices, we can have our indices array for 32. And like we said, so let's say, so now we don't want this kind of vertices anymore. Just keep this for reference for now. We only want 4. So anything that's repeated, we don't want it. So this is repeated. Bye-bye. And then this is repeated. Again, bye-bye. We only have 4. We don't have duplicates anymore. Each vertex is unique. So this is our, let's just maybe arrange them in some order. Let's have the same order we have here. So top left is 0. So top left is up and to the left. So it's this one, correct? And then top right is this one. And then bottom, at least in this case, yeah, so let's switch those around. So we'll have this as 2 and this is 3. Okay. And then this is correct. So this is essentially index 0, index 1, index 2, index 3. Right. So we will draw 0, 1, 3, and 1, 2, 3. Right, so this is our array. So our array will say draw please vertex 0, 1, 3, our first triangle, and then draw 1, 2, 3, 1, 2, 3. Then I think we can do gl.unsafe just pointer to indices. Takes a slice or pointer. There we go. Let's see. Does it do anything? Does it break? Right. Let's see. Where did we go wrong? So we do have 1, 2, 3, 1, 2, 3. We do have 6 indices in this case. I'm not sure. So let's go look it up. This guy's not okay. Okay. Row elements. Yeah, we did specify GL triangles. Yeah. The number of elements to be rendered. Should we do 2? Yep. Let's see. We do 2. We need a good doc, honestly. It has some actual explanation. Okay. GL draw elements. Index vertices, draw elements. Let's see. These are all copy paste of each other. And okay, GL row, and it's just don't think we need to load these. Don't think so. And we have our vertices. Oh yeah, so our color stuff is wrong, is of the wrong length because we only have 4 now. So we only need 4. 4 of this, 4 of this, 6 of this. Let's see now. Nope. Still wrong. 0, 0, 1, 3, and 1, 2, 3 indices. Just don't know if we need it. It does take a slice. Let's confirm. Yeah, it's not. Okay. Let's try to read a bit more. So you have, yep, this. Yeah, so it seems we do need another buffer, right? I was hoping we could avoid that, but let's do that then. So this is, it's called an element array buffer, right? It's the same thing, it's the indices. So I just call it indices buffer, it's array buffer, right? And then let's see where we do our buffers. Just shrink this. Oh. Set attributes, do these. Okay, so in here, let's generate another buffer. And I think it can be independent from the others. Yeah. And let's take not sure then for loading it why it's taking this. Oh, it's an offset. That makes sense. So I assume this is an offset. Okay, so now let's have our indices. Please take those. They shouldn't be floats. That's another thing. They should be ints. But for now, I hope it works with these. Buff type. Vertex. Okay, and data type. Well, there isn't a lot of point in data type if we're always passing float 32. Well, for now, say that, and we are passing this, so create buffer, and how do we bind buffer? So we bind to the GL type, which is array buffer. Yeah, this is not correct. We should take actually, yeah, we might, I think we need a new function. So buffer usage, and here we are hard coding the, we can look, yeah, we can do that actually. Buffer type, data type index. So we can do this. Data type. Data type should be an int 32. Let's do gen buffer int 32. This one. Let's copy it. Because we want to, these indices are always int. Doesn't make sense to be sending floats. So let's do an int 32. And then we have this and the type. The type is what? It's a buffer type. And the buffer type we said could be any of these. So honestly, we can decide what this is depending on the buffer type. So buff type. So in here, we can say if we can say GL type, right? GL type, we're doing buffer GL type. And then we can switch on the buffer type we got. And if it is buff type index, so we can default, like honestly, we can default to this. We can default to this. And then if it's this one, we can say GL type equals buff GL type indices buffer. Right? And then here we do GL. Yeah. But this is a weird place for it. Maybe for each type. Let's keep it for now. I mean, we can improve the code later, but yeah, so we have now a GL type, and we, yeah, this is not used anywhere else. So now we are doing the correct type here and the correct data. Element size into length of data. So now we have our indices. It can be int32, gen buffer int32. It's a static buffer, it's index, and it's int32 data. And it should be, you know, done with all the nice magic that we have with VAOs, bind to the VAO and so on. And in the end, it should hopefully recognize, because now when it's binding, it's going to use the GL type, which is an element buffer. It's going to know, oh, okay, this is something else. Right? It's going to know it's a different kind of buffer, and so when we come to draw, we can use draw elements. All right, let's see. Maybe this is good enough. No, oh, okay, what is this? Unknown buffer type instead buffer type 3. Okay, yeah, we need to add it. This is one of the systems I would like to kind of redo. Buff type index, and now we need an index buffer. Index buffer, right? Let's do it. No, not yet. So, oh, this is an int. Oh, still giving us black screen. I wonder why. Yeah, count is this, offset is 0. We're doing draw elements. Render problems from array data. Shouldn't. Okay, activate. Is bind the VAO. Okay, so we bind it, we create the buffer, and then we have some data, right? Let's debug this. Let's see. Oh, I did I not save? No, still the same. Okay, let's debug. Any questions, guys? So far, I think there are so many different topics coming in today, but yeah, this is the nature of it. Come on, are you not going to hit this or what? Come on, you can do it. Okay, I'm not sure what the issue is this time. It's not running. Okay, stop this one. Stop all of them. Launching package is really odd. Launch package. Yeah. 1, 2, 3, 4. 1, 2, 3, 4. Type is index. And while it's loading, we can check this. This is element array buffer. Element array buffer, yep. Oh, finally. Okay, so our VAO is one. Bind it, then we create. We have 3, looks good. And okay, did that. And then we have our buffer type. Let's step into this. Yeah, correct. Turn. Then we set the buffer. There we go, correct. Okay, looks good. Okay. So we have the GL type. I just want to know that this matches array buffer and indices buffer, element array buffer, right? This is correct, element array buffer. Right. And because when we buffer the data, we also need it, element array buffer again with static draw. Yeah. And then we have 4 bytes into the length of the data, which is 6. And then a pointer to the data and static draw. Right. And then we unbind the VBO and finally unbind this one. Okay. This looks correct. I don't see. Activate the buffer object, which binds the BAO and then draws this. Yeah, it looks. Wait, why are we generating? That's weird. Okay, step out. Yeah. We still see the black screen. So we have top left, because our ordering should be correct. That's one thing. Top left and then top right, bottom right. Oh, bottom right. Yeah, bottom right and bottom left. And then to draw these, we go essentially top right, yeah, top left, right, and 3, then 1, 2, 3. Yeah, this looks okay. We convert. Which is global state. So the array buffer is a global state. The element array is part of the current vertex array. We bind this vertex array. So it seems we have to bind for index type unsigned bytes. Okay, so maybe int is invalid. So we need unsigned int. Okay, that's potentially one reason. So we have here, we'll call it a uint, a uint32, and so and the data becomes uint, and the data type that we pass becomes different. So this is a uint. Okay, we need a new type, I think. uint32. Yeah. Hey, we did not set those to type. Right. Now they're correct. So get data type info, we give a data type. Right, so where's our uint? Uint, do we have one? No, we don't. Uint matches int. So I think in Go fall through. Is that right? So you int 32 and then this thing. So you int and let's see. Nope, still. So what more details are missing? So we need the uint and we have static buffer. Let's look. I think Unity, for example, does unsigned shorts. if I'm not mistaken, at least last I remember. That's why their maximum vertices per single object is 65,000. This is one of the low level details that tells you why that is the case, and well, they're using this for their, which reduces memory usage, right? Per index, most of your objects are going to be below that, so you saved like 50% of the memory compared to this. But otherwise, we should still be able to do unsigned int. But it also seems that we do need the need to bind the vertex array, because here they're not doing VAOs. I'm not sure. So bind the vertex array, and then bind that. So let's try. Let's see. So we bind this, but since this is let's do buffer objects dot vertex buffer dot GL type, right? Okay, and dot I. So let's try what is being said there, which is bind all of these. Not sure if it's the order here. So we bind the vertex buffer and then we do the element buffer, just so kind of there is a relationship between them, similar to how we bind VAOs before I use them. Let's not unbind for now. No, that's so odd. I'd like some debugging, honestly, now. Some more OpenGL debugging utilities. Let's see. The vertex position buffer, and we're doing the indices at the end. So we have vertices. UN32 buffer type, usage static. Element array buffer, and then we bind. Oh, they are using VAOs. Okay. Triangles, 6 indices, inside sure. Ooh, in the draw. In the draw, we have a U inside int. Oh, finally. We are back, people. We are back. So many tiny little details. This is one of the things that also makes it interesting, but difficult. There's all these tiny details, like, oh, your type here was wrong, and so it was reading the data wrong or not accepting it. But finally, we're there. I don't like how the buffers work now. The API is just all, confusing. But yeah, so I would like to see if we just bind the VAO, does it still work? So in here we don't bind. It does. Okay, it does. So we don't actually have to bind this since we have VAOs going on, which makes it easier. So our only kind of bad thing here is this. Now just to show the power of this, the nice thing is now with the same vertices can potentially drop part of it. right? Or reorder it if that makes sense, just by saying, okay, you know what, I don't want to draw this. Like I maybe just want to draw this first triangle, upper one. So you can select the indices, or maybe just reorder the indices and then draw a different triangle. Like, let's think about it. If we can we do something? So let's say we have these four. We want to draw this triangle from here to here to here, which normally we don't have, right? So this is index 0, 2, 3. Like, imagine completely flipping it, right? 0, 2, 3, and so you can do it like this, and then we can draw this upper one, which is 0, 1, 2. Right? So it's like, okay, so you can do 0, 2, 3, 0, 1, 2. We should still see this. See, now the colors seem more diffused here, right? Because I think the vertex is now going along, like the way it's diffusing is more, just because where the line is being drawn right to the vertex. So there are all these interesting ways, essentially, which we can do this. So we don't need this anymore. These we can remove. Like this. All right, so we have now only 4 vertices, only 4 colors. And now that we have this, let me just do this part. So buffer type and GL type, why don't we just combine these? We make a way when you give us a buffer type that to get the GL type for you. Does that make sense? I am not sure. Because where do we ever use, not buffer usage, but the GL type? Buffer usage, buffer GL type. Right, and now we can maybe have a function here that gives us the buffer GL type, maybe, and buffer type, buffer usage. Yeah, buffer usage we need, buffer type we need from the user. I just don't want to have kind of the code looking different, and hopefully once Golang releases generics, we can combine these. It's coming soon. Right, so we can maybe move this and have a function. Not sure if it's completely correct, but for now we can use it. So buffer GL type get GL type, right? Oh, sorry, it's buffer type, I think. Yeah, from the type of this. From the buffer type, yeah. Func vt buffer type get GL type. Get buffer GL type and returns a buffer GL type, right? Then we can just have the switch statement, essentially, which we had below on the buffer type. And so before we said that if this was an index buffer, right, we wanted to say that, hey, this is a buff GL indices buffer, not a normal one. And we can have a default case. We can return unknown. It's 0. Okay. And call this unknown is equal to 0. Okay, so now we can return the field type unknown. Should also log a warning. So logging dots warn unknown. Where is this? We can steal the message from here. Unknown data. Unknown buffer type. Buffer type is BT. And here we have print line. Okay, so we have now this thing, and then in the other case for the vert and color, we can just do case vert pos, right? Returns and a buff GL type array buff. I think it makes more sense to get this up there just before, right? And then the color buffer is just a false one. So basically, if it ends up here, it goes to the next one, which returns another buffer. So you have now all the three. Right. This might array buff. Just use buff GL type array. I think the buffer word is redundant here. Buffer GL buff type buffer. Yeah, buff. Even here, buff GL type. So buffer is kind of our buffers, right? So we have our own thing. Then what is the buffer's GL type, and from our buffer we can transition to the GL type thing. So buff usage, maybe even call it GL usage, and then we have an error. Right. So in here we can do buff type that we have dot get GL. There we go. And then in gen buffer we also don't need to hard code type array. So instead of hard coding type array, we can do this thing. And here we do this, and so they are exactly the same code, kind of unfortunately, but the data type we're passing is different. That's it. That's really it. Everything else is the same, exactly the same, which is as it should be. I think this is about good for today. Let's just run, make sure everything is still good. Very nice. You can see the seam in the middle there. So we have transformation matrix today. We are loading OBJs to some extent. I think what would be interesting is really quickly in the loader. So when we're loading this OBJ, so now we're loading vertices, we can load these faces, which are the triangles. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So the nice thing is these are already indices. So if we have a look, so face elements, so they are given in the format vertex index, texture index, normal index. So we only care about the vertex index so far, and it starts at 1. So we get it, we -1. That's our indices array, which is very nice. So in our loader, we can actually give back a guard spots, right? I don't know what to call it, but we can give back a type obj info, I guess. I'm not sure. We can think about how to structure this in the future, but at the very least, we're going to get vertex positions, right? We have indices or triangle indices, right? I think for now that's it. And so we can return an object info, and object info. Yeah. Right. What's wrong? Leave the name here as well. Okay, so we have our error. So instead of adverts, we're going to directly use this object info. Object info dot vert positions. And just return object info. Now this should give us the exact same results as before. Oh, actually, the color needs to change now. This is correct. Oh, we're not using it. So let's do this. Object info, and the vertices are just these. But we also need to load the faces, so we can have another case f, right? And f, again, we're going to split the spaces. Yeah, if it's an f, then that and everything else. Yeah, why did we split twice? We split once. Okay. So again, we're going to split faces strings, and then so if we assume we always have 3, we can split by this, and then like this is, we need to split first by the spacing, exactly like this, and then we have, this is 1, 2, 3. So let's do that. Get func get vert index from face. So we give it a string, right? And we get back an integer. So once we have split by the spaces, this is index 1, so we can do object info dot indices dot append append what get vertex index from face, and here we can just give face a string 1. So 1 is going to give us all of this, and then we can simply say, so it's strings.split, split f on this, and then let's see. We actually only care about the first, so we can say split n and split only 2. I think it's a bit more performant. And we only care about the very first one. We only care about the 5. So this is index string, right? And then we can return, actually, we need the actual index with an error, which we don't care about right now. Yeah, let's do it. We do the same thing. So string converts parse float, right? Index string 32 bit floats, then error, and logging. So we are assuming the thing is valid. Otherwise, we can return some -1 or something. Invalid base index. And here it's just the v. And we can do error another v. So the face that is invalid is index string, and the error is this. Then we can return float 32 of index. Oh, actually, yeah, it's simple. A to I. There we go. Very nice. So this is a list of 32, and this can be an N32, and this can be that should be it. Then we just do it 3 times. So once for each index. So 1, 2, and 3, and we actually do need to -1 because it says that these are they start counting at 1, not at 0. So we need to -1. I think with that we can where is this thing here? We can info.logger.printf obj.info dot triangle indices. Ooh, 3 is out of range. So here face string. Oh, okay, it's already we already split twice. Split 1. Yeah, it's already split. Have that. Okay. Invalid face index 5. Error null. Right? Oh, of course. If error is not equal to null, then we have a message. Should actually also eventually return -1. So these should always be uints, as we just said, and so this is 0. Potentially panic, but yeah, let's see. And then this is a uint. This is a uint. Let's get those. So we have our object file. So we should see 420, right? 273. Okay, these look correct. These look absolutely correct. And so we're actually loading the object. So instead of these, let's take this here, right? So vertices are actually these, and indices, we can do try indices. Now in 6 we need to put the actual number, but let's just see. Okay, maybe print line len of indices, just so we can. Oh hey, we have part of an object. Nice. So we have 36 indices. So in here we're going to say please draw 36. There you go. Our colors are wrong. Is there color data here? I don't think so. I don't think so. So maybe we don't do color data. Where's our shader? Let's go to the shader and no out. I think we can leave it. Just that in the frag we won't use this. Instead of this, going to be say all white for now. And I think in Blender you can specify, you can tell it to export color data. Here we go. It's so nice. And then here we don't do colors. This is not declared, don't use. Buffers, oh yeah, and set attribute. Okay. Awesome. So we are essentially, I think, again seeing now it looks more correct. We're seeing, yeah, we're clearly seeing this part of it. It's like we're zoomed in and we're seeing this part is very clear. So we actually loaded a 3D model, which is very cool. We can maybe shrink it and move it to the left. We already shrink it by half. We can maybe translate it by -1 on the left. Let's see how that goes. Yeah, there you go. So we have the full model and our translation matrix working really nice. So let's do again, like shrink it even more. So we are loading a proper 3D object from 3D modeling software. And let's move it on. There we go. Beautiful. So we have 3D object loading, rotation, translation. We can maybe play with some inputs next time. But yeah, this looks really good to me. I think this is it. Maybe you can play with rotating it around maybe x-axis. Rotation in this case would look bad just because we don't have all the, yeah, see how it's cropped? We don't have the projection matrices correct. But I think it's kind of showing more to our end, and we don't have lighting. So we need normals. We need to read normals as well. We rotate 90 degrees. We should see maybe top face. Yeah, just see the top part. Yeah, this looks good. This looks really nice. So we have this. We're not loading cards, which we can do next time. I think this is a really good stopping point. Yeah. I think our buffers class looks better. Is there anything quick that you can do? No, this looks okay. Buffers data type should be more complete now. You want to enter the same, and yeah, float. We have a loader now, and these. All right, this is it for today. Thank you everyone so much. And we'll see you next week. Have a good day.